Okay, good afternoon. My name is Juan Alfaro, and welcome everyone to this talk. The topic we are going to talk about today is related with this year's advances on my thesis, with title Design of a Smart Geometry Variation Morphing Wing for Optimized Drone Performance, supervised by Rodrigo Castellanos and Carlos San Miguel. The entire project has been developed in the National Institute for Aerospace Technology and in collaboration with Universidad Carlos III of Madrid. Okay, first let's start with the main challenge of the thesis, which are gusts in non-conventional regimes. For vehicles like UAVs in urban canyons, a strong gust can appear, causing great instabilities to the vehicle, as can we see in this video. These disturbances are no longer perturbations. In fact, they are flow reorganizations around the wing, which can cause several effects, such as transient lift losses and separation, among others. These effects can be suppressed by innovative solutions like active control, as the one shown here with active flaps, but a rigid flap along the span is not enough. That's the reason of the appear of the target of the study, which is building a smart wing that can adapt in real time to changing flight conditions. This smart wing is built around two main concepts. The first one is the continuous camber morphing for a smooth shape change along the span, and the other one is closed loop gas load alleviation based on pressure sensing and deep reinforcement learning. Okay, so now I can present the three main pillars of this entire project, which are the following ones. First, we have the sensing part in order to know where and how to measure everything around the wing. Then we have the actuation part for flow and geometry control, to finally end with the control part, which is related with machine learning, reinforcement learning, and closed loop applications, to finally end with the intelligent morphing wing. So first, let's start with the sensing part. The main idea is quite simple. No models is more than its sensors reveal. In real life, we have to take advantage of minimum information. This can be translated into the experimental world, where sensor placement is crucial. For this, I've been working with a differentiable sensor placement optimization algorithm, DSPO, which is a numerical tool which uses an MLP net, which reconstructs the full field while the model and the sensor locations are co-optimized. This is first a numerical approach, but with the correct data sets, the results could be extrapolated to the experimental environment in order to know where to place the sensors in the real model. After the optimization, we have found really interesting results. For the NASA CRM dataset, we have performed 50 runs with 4 sensors in random initializations, and the final sensor position revealed that the algorithm is capable of detect the most interesting aerodynamic areas where the dominant effects take place. Also, the algorithm is really nice in field reconstruction for the pressure coefficient around the wing with minimum error, and this error is minimized, obviously, with the increase of the number of sensors. For the future steps in this numerical approach, we want to extend to 3D flow field reconstruction, target more complex data sets, and also move toward gust environments in order to move to the experimental campaigns and use this useful data. Once that the sensing part is partially covered, we are going to move towards flow control in an experimental condition. The main problem that it's going to be target is low Reynolds number environments where airfoil separation occurs at moderate angle of attacks, creating weight momentum deficit, meaning that the drag increases. The approach we are going to use is re-energize the separated shear layer fast and locally by the use of pulse jets in the upper surface of the wing. As the actuation parameters are non-intuitive, we are going to use data-driven optimization tools to find the optimal actuation parameters. So why flow control? To start with this, well, pulse jets are quite nice, acting directly and fast in the separated shear layer compared to geometrical changes, which are created by the morphing by itself. But this other solution is also beneficial for other type of conditions, so both solutions must coexist in the same wing. That's the reason because we are developing both solutions in parallel. In terms of the experimental setup, I will go fast in here. We are performing experiments in an open-type wind tunnel. The airfoil, it's a NACA 18 placed vertically at 6 degrees of angle of attack, and 3 fast actuating valves are the ones creating the pulse jet actuation in the wing surface. The core base Reynolds number is 50,000, and we are measuring the performance of the actuation in the wake using particle image velocimetry. Here you can see the pneumatic line feeding the valves. Each of we are using 3 valves, and each of them are connected to their respective slot in the wing, as you can see here. In terms of the flow field measurements, as I have said before, the wake is evaluated using particle image velocimetry at 3 chord distances from the trailing edge. For each actuation, we are taking 200 images, we are doing the average of them, and we are computing or extracting the wake profile from the center of the image. And here you can see how is the story in this experiment. When the control is off, we can see in the red line a velocity deficit in the wake, which is reversed with the control on, creating a velocity excess or a thrust generation. So with this metric, we can evaluate how well is performing our actuation. In order to find these parameters, we are going to use machine learning algorithms in this experimental environment, specifically with multi-objective Bayesian optimization. We are going to optimize 2 cost functions, which are here, J1 and J2. J1 will account for drag reduction, creating or promoting thrust generation, and J2 will focus on creating a wake the most similar to the free stream condition. In this campaign, we are going to launch 75 Latin hypercube sampling control laws to explore the domain, and then we are going to evaluate 329 individuals in order to minimize the global J, which combines J1 and J2. The control parameters are for each valve, the frequency and the duty cycle, for a total of 6 control parameters, where the frequency goes from 5 to 500 Hz, and the duty cycle covers almost the entire range of the actuation. Once the experimental campaign is launched, the multi-objective Bayesian optimization is capable of finding a well-defined Pareto front of non-dominated control laws. All of the individuals are colored by the UCY, the Utopia Closest Index, and in the right you can see how the wake how the wake behaves as you move in the front. For the case of J1, if you minimize J1, the wake creates like velocity excess, generating thrust, and if we minimize J2, as I said before, the wake behaves mostly like the free stream condition. In the middle of them, we can find the sweet spot where both of them are minimized. In order to understand better these results, the work in progress is based on PIB, stitching PIB, patch POD, and wake analysis with hot wire anemometry. Okay, once we have finished with flow control, we have to move towards geometrical changes with the morphing wings. The goal is to create a wing that can reshape itself. So we are creating a fishback morphing wing. It's a wing with a compliant trailing edge design inspired by Wood's work. It is 3D printed, combining rigid and flexible materials, and the mechanism is driven by a tendon pulley system. It is in final prototyping stage, so we are ready to put it into the wind tunnel. The design allows to insert a modular leading edge to host the sensing and flow control part. So we can insert pressure ports, slots to combine both works being developed, the DSPO and the slot wing. And finally, we have to create the gas environment in an experimental way, so we can understand in real life how gas interfere with our wing. So we have developed in our wind tunnel an in-house gas generator based on two NACA 12 vanes, which oscillate, creating one cosine gusts with small gas ratios for the moment. They have been characterized using hot wire anemometry and PIB stitching in order to know how the flow is moving along the test section and where to place the wing in the most interesting place. Okay, so with everything ready, the next step is about to close the loop, integrating the morphing wing or a flap wing with all the sensors incorporated in them to downstream the generator in order to control the effects created by the gusts. This should be closed loop and combining all the work developed during the thesis, which is sensing, actuation in flow control, and actuation in morphing wings. And now to conclude, here's some work being developed. The DSPO and PulseJet paper are under development, but during this time I have been working with my team at INTA and UC3M in different papers related with flow control, drag reduction, heat transfer enhancement, and also in different conferences showing this type of works. And also there are some ones to be confirmed for this year in Madrid, and yes, mostly in Madrid. So this is everything. If you have any questions, don't hesitate to ask. Thank you.